Okay. Actually, I get ready for the lectures, and I try to make sure I'm ready. And so I did this about a couple hours ago, and I've already forgot what the lecture's about. Oh, yeah, standard molar enthalpy of formation. So enthalpy, of course, is the H's. So we're going to be talking about delta H's. Now, I think I took the next slide, and I broke it out. Yeah, you have a bunch of that next slide's coming. But before that slide, this is one of those things where the standard molar enthalpy of formation, in the word, you can break it out. It's the formation of 1 mole of compound from its elements in their standard states at standard conditions. So I'll just kind of leave it up there like that. Yeah. It's what I started to say, it's one of those things where within the word, the definition kind of screams at you. So, okay, so it's the formation of 1 mole, so it's formation of 1 mole, okay, from material in their standard state. I don't know if this is really the order, but it's the enthalpy, and that's your delta H. So we'll see what that looks like. Now, standard. We talked about that. That's the naught. So H naught would be the enthalpy at standard conditions. Wait, did that wrong, sorry. I should have gone down here. Standard conditions. That's your H naught. Anytime you see a naught, that's standard conditions. And for thermodynamic, we said for thermodynamic problems, the pressure is 1 bar, which is about 1 atmosphere, and the temperature is 25 degrees Celsius. So that's going to kind of be revisiting it. Okay. So these important enthalpies are denoted as change in enthalpies, delta H of that little F subscript means formation. And of course the naught means standard temperature and pressure. Okay. So it's basically the buildup of 1 mole of a compound from the elements in their standard states. So what is the standard state for an element? Well, hopefully, if you think about it, you can try to picture that element, anything on the periodic table, any element on the periodic table, try to picture it at 25 degrees Celsius, which is about room temperature, and 1 atmosphere, which is about normal pressures, okay, of the Earth at its surface. So whatever that standard state is. By standard state, we mean, is it a solid? Is it a liquid? Is it a gas? Okay. And of course, the naught means 25 degrees Celsius in 1 bar. So here's another thing to kind of stick back somewhere. The standard molar enthalpy of formation. Standard molar enthalpy of formation. This thing right here, the standard molar enthalpy of formation of any element that is already in its standard state is 0. So that's kind of awesome. Standard molar enthalpy of formation of anything in its standard state, standard temperature and pressure, is 0. And we're going to see that coming up. Standard molar enthalpy of formation. It's got a rhythm to it. Standard molar enthalpy of formation. And you might recognize these from, these were our puzzle pieces from Monday's lab. Okay, we had 1, and then we made a 1 prime. We had 2, made a 2 prime. We have 3, made a 3 prime. Remember, we kind of had to manipulate them to get our overall. In that case, it was reacting benzene with oxygen to form carbon dioxide and water. So do you see that this is the molar formation of 1 mole. How do I know it's 1 mole? The coefficient in front of each one of these is implied 1 mole. And if you were to go ahead and evaluate the reactants, carbon and hydrogen, does carbon seem like it's a solid? I don't know if you know which allotropic form, but trust me, it's a solid. Graphite is its standard state under standard thermodynamic conditions. Okay, hydrogen, it's a gas. That works. Carbon, again, graphite, solid, oxygen, a gas. Okay, hydrogen, a gas, oxygen, a gas. That's all we need. So that is actually the buildup of 1 mole of compound from the elements in their standard state, standard conditions. So these are, let me put it another way, These guys over here, these are all standard molar enthalpies of formations. They are all standard molar enthalpies of formations. So that's kind of fun. That's our puzzle pieces. So we're going to get a try at it, kind of looking at a reaction, and the enthalpy for that reaction is given. And so the question is that enthalpy of that reaction, does it represent a standard molar enthalpy of formation of anything? Okay. So I think I've got 4 here coming up. And here we go. This is the first of 4. Standard molar enthalpy of formation. And to me, you kind of go through the checklist. Is it forming 1 mole? And people think it's forming 1 mole of compound. Does it look like it's from their elements in their standard state, standard conditions? As far as we know, that looks good. So you can put a check mark next to that one, or however you want to denote it. This actually is a standard molar enthalpy of formation of the compound methane. That's it. Okay, let's look at the next one. Okay, so the checklist. Is it forming 1 mole of compound on the product side? Looks to me like it. Are our reactants in their elemental form? I guess that's a separate check mark. Are they in their elemental form? PbCl2. Yep. Does lead seem like it should be a solid? Chlorine seem like it should be a gas? Yes. Okay, so in other words, this guy over here, okay, this heat of this reaction is a special heat of reaction. It's the standard molar enthalpy of formation of, let's go ahead and I'll put a comma, of PbCl4. How's that? So it is. That one is, that one is. Well, you know some of these 4 can't be. So if it can't be, let's see what's wrong with it. So this is our third of 4. Is this the formation of 1 mole of compound? I'm liking it. Yep, 1 mole of compound. The reactants, are they elements? No. Right. So this right here, this means it's not the standard molar enthalpy of formation. It does not represent the standard molar enthalpy of formation of PCl5. Right. I mean, it's a great enthalpy of reaction. I'll go ahead and just do RXN. Okay. That's awesome. It totally is. But it's not a standard molar enthalpy of formation of anything. Okay, 4 out of 4. All right, is this the formation of 1 mole of compound? No. So right off the bat, this means no. So it's a standard molar enthalpy of the reaction of this. Remember that the heats of reactions or enthalpies of reactions are specific to a balanced equation. So that's great, but it's not the standard molar enthalpy of formation of strontium oxide. Strontium 2 oxide.
What does the RXH stand for?
Reaction.
Okay.
But otherwise, it looks pretty good, right? Okay, that's kind of how that goes. All right, so I was getting ready for today's lecture, and I'm like 42 slides? Are you serious? But check out like the next slides. Oh my gosh. We're just going to kind of buzz through those, okay? Some standard molar enthalpies of formation. I guess it's coming up. So, standard molar enthalpies of formation. And to me, one of the things when you're looking at a table, you just kind of have to get your bearings. This is actually 2 sets of substances. Substance over here, how much energy per mole of material is released. If it's negative, it's released, right? Exothermic. And if it's positive, it's endothermic. Okay, so this is where I thought I was. This is where we have 10 billion different slides that all go blah, 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 blah. Okay, and if you have to use like these standard molar enthalpies of formation on your homework. You have to have really good eyesight to read them from there. You should be able to find them like in appendix in the back of your book. So here we go. That starts with inorganic substances. That could be an element or an inorganic compound. There are actually 3 columns, and they all deal with thermodynamic issues. Okay, so that is enthalpy. H is enthalpy. G is Gibbs free energy. And I know in biology you guys deal with Gibbs free energy. I'm not quite sure why. But that sub F with the G means Gibbs free energy of formation. And then the last one is my favorite one, entropy. And this is where I don't know. I wish that to me, enthalpy, the H, and entropy, the S, sounds so similar. And they are both in kind of, they both deal with thermodynamics. But entropy is kind of like chaos. I love entropy. And Gibbs free energy and entropy we won't look again at until actually the end of Gen Chem 2 when we talk about cells. So anyway, so just focus on that first column, okay? And here's the second slide. Again, inorganic substances. It could be an element or a compound. And then I just went ahead and I went to the last slide. So if you want to find this slide, okay, this is a few slides from now. It's all alphabetical, okay? So the 3 columns. And we talked about that the standard molar enthalpy of formation, I love saying that, for an element in the standard state is 0. So standard molar enthalpy of formation of zinc, 0. Uranium, 0. Helium, it's all 0. Cool. And then we switch gears from inorganic to organic. And organic basically deals with specific nonmetals, carbon, hydrogen, oxygen. So here's some organics. And again, we have the 3 columns. Notice we've added, or your textbook has added a line, I guess the other one had the line in the name too. Not sure. Okay, so there's a couple of those. All right, blah, blah, blah. Well, let's get to a problem. You want to be able to think in terms of doing this. I'm trying to think if you'd ever have to do this on a test, and I would probably say yes. You need to be able to kind of think through this. Make your own reaction that represents a standard molar enthalpy of formation, okay? So we're going to pick on ethanol. And so to pick on ethanol, the formula is C2H5OH. So we need to go gather what is carbon in its standard state. Well, it's not a diatomic. And in its standard state, we decided its solid specific allotropic form is graphite. Okay? Hydrogen and oxygen are both diatomic elements. So in nature, they'll exist as H2 and O2 respectively, and they'll be in their gaseous state. So those up there are going to be our reactants when we write this is our reactants. When we write our standard molar enthalpy of formation. That's it. So then we could start like this. We could go ahead and on the product side, remember we said that's the formation of 1 mole. So when we balance this, and we will balance this, we have to have a 1 over there with our our ethanol, sorry. So this is going to have to be a 1. Usually I don't really care as long as you balance it and your set of stoichiometric coefficients gets the same number of atoms of each type of element. On either side of the reaction arrow, I usually don't care what your set of coefficients are, but that has to be 1. Okay, so then let's go ahead and jot down the reactants. So we'll put down carbon, solid, graphite, hydrogen, 2, H2, the molecule, gas, and O2, gas. So now it goes back to, I can't remember what unit that was. Is it unit? I don't know. But when we balanced equations, so then we got to balance this. And if you balance it, you'll come up with 2 moles of carbon, still warm, 3 moles of hydrogen, and 1/2 mole of O2. You did a fine job opening that window up, Brand. We're going for a second one. It's hot. Okay. So, that's to say that when you wrote this, okay, this is what she should have at the bottom of the previous page, that enthalpy of that reaction is the standard molar enthalpy of formation of C2H5OH. Okay, so I don't know how you want to write that down. So the enthalpy of that reaction that you just wrote is negative 277.0 kilojoules. So, in this semester, this is the first time I've done that. I like subscripts to kind of say what you're talking about. So the standard molar enthalpy of formation of C2H5OH is negative 277.0 kilojoules. Cool. All right. So just for kicks, I went out and proved it to you. This is like one of those last two tables that we looked at because, of course, ethanol is an organic substance, so we'll find it there. And there's your negative 277. Oh, was it 0.0? Oh, I'm not sure why, because you'd be like, all right, Mrs. Snipes, notice you have a 0 here, and the table says 7. I don't know. I couldn't tell you that. Close enough. Okay. All right. Switching gears just a little bit. So if you have to find the standard molar enthalpy formation of anything, you can use those tables. But let's just say that what you're looking for is not on the table. Okay? Then you can do it this way. Oh, that's not right. Oh, darn it. Let me put this whole thing up here. I got that wrong. Scratch that. Let's just say you want the heat of a reaction. You want the enthalpy of a reaction. Final answer. Notice it's just any. It's not the formation of anything. Standard molar enthalpy of formation. It's just any reaction. Well, if you have your table, and for all of your products, if you have their enthalpies of formation, and if for all of your reactants you have their enthalpies of formation, then you're set. I'm going to kind of show you how this works. Of course, we ran into the summation before when we were doing the average atomic weight. That capital looking E things means summation. So notice we're going to start with the product side, and we're going to do a summation, and then we're going to turn our attention to the reactant side, and we're going to do a summation. So you see the A and the B. The A and the B are the stoichiometric coefficients from the balanced equation that you're trying to find the enthalpy of the reaction for. So let's just do one. I'll show you how this works. So this might look familiar. This is actually what we did with Hess's Law the other day on Monday. We combusted benzene, and we formed carbon dioxide and water. Let's just say you don't know the heat of that reaction, which we do if you go back in your notes. Okay. So if we don't know that heat of that reaction, but we do know the enthalpies of formation of the two reactants and the two products, and they're listed here. Now, coming up with the heat of a reaction like this, it's really easy to get mixed up with what goes with what. Another thing I've seen is it's really easy to get our signs mixed up, our negative and our positive. Another thing I've seen is it's easy to kind of lose sight of, I'll put an R over here, and I'll put a, darn it, nope, no, I won't. I'll put a P over here for products, and I'll put an R over here for reactants. Final answer. My P's and R's kind of look similar, don't they? And it's always product, the summation of the products, minus the summation of the reactants. products minus reactants. So we're going to use those. So here's how this looks. Again, it's easier to show you than to explain it. The other thing, if you want to put exam on here, you can, because I guarantee you that there will be one of these on your test. Okay, so here we go. Let's work this thing. Like working most chemistry problems, your important task is to communicate with me how you're working it. So be careful. I like to kind of do it into kind of two parts. I focus on my products because that's actually going to be the first term that I subtract my reactants from. And I come up with a summation. I need to represent my CO2 and my H2O. The A's, I said, were the stoichiometric coefficients. So we get 6 moles of CO2. The standard molar enthalpy of formation is negative 393.5 kilojoules per 1 mole of CO2. So moles of CO2 cancel. I'm just left with units of energy. Now I'm going to invoke the summation part, so because I need to turn my attention to my other product, which is H2O. So it'll look like this: 3 plus 3 moles of H2O times its standard molar enthalpy of formation, which on the previous slide or from the table, you get is negative 241.8 kilojoules of energy per mole of H2O. Moles of H2O cancel, we're left with units of energy. Notice we have 2 exothermic thingies there, okay? And we round according to actually decimals. So we're allowed 1 decimal in our answer. So adding those together, we get a negative 3,086.4 kilojoules of energy. So that is my product side. And then I usually maybe draw a line or leave that as its own little paragraph. And now I'm going to turn my attention to the reactant side. So on the reactant side, I had 1 mole of C6H6 times, it's a positive 49.0 kilojoules per mole of C6H6. That's the standard molar enthalpy of formation of benzene. Now we need to invoke the summation part, so we need to add the O2. Now, the fact that it's O2 gas means it is actually in its elemental form, it's in the right state, standard conditions, so actually it's 0. So I could put 15 halves moles O2 times 0 kilojoules per 1 mole of O2. Sometimes students would say, well, Mrs. Snipes, I'm adding 0, so do I have to include that term? And I would say, student, do you want to get all your points? So it's a free country. I think so. So of course, when you add that together, you get the 49.0 kilojoules of energy. Okay, so we have the reactants and we have the products. So it's reactants, this is where I've messed up before, minus, darn it, we have the products, then we have the reactants. It's the products minus the reactants. Okay, so this is what that looks like. So now we're ready to finish up one last subtraction for the enthalpy of this reaction. So it would be negative 3,086.4 minus 49.0 quantity kilojoules. And you're subtracting something from a negative, so it's kind of like adding them and carrying along the negative sign. I don't know, however you want to think of it. Okay, again, we round according to decimals, and you should get negative 3,135.4 kilojoules of energy is the energy release associated with that combustion. And that's using the standard molar enthalpies of formation of the products and the reactants. All right, so again, I told you you wanted these on the test, and I really do believe that homework is a way for us to make sure we're all on the same page with regard to getting full credit on your exams. If you get by with it on your homework, then you might be able to get by with it on the test. All right, let's take a look at these. straightforward, I think. I say they're straightforward, but like I said, it's just easy to make silly mistakes. The type of mistake when you get your test back, you're like, oh, are you serious? Okay, here's what I got. Okay, so we don't know these heats of reaction. Okay, so you're supposed to come up with the heats of reaction for A and B. But you can use your tables or whatever to get the standard molar enthalpies of formations of the reactants and the products. Okay, it's always products minus reactants. So I went ahead and kind of a little bit overkill, kind of showed you how the first one looks. So I would clearly say products, blah, 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 reactants, blah, 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 and then do one last subtraction. I really would. So I kind of showed you what we did for A. So you guys are probably okay with the fact that, like anything I put a star next to, that is what you get from a table. Get that from a table, get that from a table. Sometimes students are like, do I have to memorize that? I'm like, heavens no. Get all those from a table. Well, maybe not the for hydrogen gas, but, and then one last subtraction, okay? So it's always products minus reactants, and then that little brown circle over there, the difference would be the enthalpy of that reaction. Then you're done. And then my hint for B is similar to A. And my hint for the next one is similar to 79. So you guys have the answers to these odd problems, remember? Under doc sharing is a PDF that has these. I think it's a PDF. Now it's starting to cool down. Okay, so then this one, like I said, similar to 79. And then I just went ahead and put your, okay, so any questions? All right, well, that's about as far as I want to get again today, so hope that works for you. And Friday we should be in good shape to finish up Unit 3.
And so just these two
Yep.
problems on